What if I told you that the future of ultra-fast software development, of breakthrough optimizations, is already here, and it's powered by AI? Well, get ready, because today we're diving into a story that literally blew up on Hacker News. A story so compelling it sounds like science fiction. Yet it's very real. We're talking about how AI, with the help of auto research facilitated by OpenAI's Codex, achieved an mind-boggling 232 times faster kernel performance. Yes, you heard that right, 232x faster. That's not a typo. Before we unravel the how, let's set the stage. Optimizing critical low-level kernel functions is often considered the Everest of software engineering. It's a domain where every clock cycle counts, every memory access pattern is scrutinized, and every instruction can make or break performance. Traditionally, this process involves weeks, sometimes months, of painstaking manual research. You're sifting through obscure academic papers, ancient CPU architecture manuals, poring over disassemblies, running benchmarks, and engaging in endless cycles of trial and error. It demands a deep, almost encyclopedic knowledge of computer architecture, operating systems, and assembly language. The sheer cognitive load, the time investment, and the specialized expertise required make it a formidable challenge for even the most seasoned engineers. You're often working in the dark, making educated guesses, and hoping to stumble upon that one golden optimization. But what if you could compress weeks of this research into hours? What if you had a tireless, virtually omniscient assistant that could instantly recall obscure optimization techniques, suggest relevant algorithms, and even write boilerplate code tailored to your specific problem? This is where the concept of auto research with AI enters the picture. Think of tools like OpenAI's Codex, a sophisticated AI model trained on a vast corpus of code and natural language. Not just as a code generator, but as an incredibly powerful research assistant. It's like having an entire library of programming knowledge and a team of expert consultants at your fingertips, ready to synthesize information and propose solutions to highly complex problems, all in real time. My workflow with Codex wasn't about simply asking it to make my kernel fast, it was a highly iterative and structured dialogue. I started by feeding Codex the existing, unoptimized kernel code, describing its purpose and the perceived bottlenecks. For example, I might prompt it with, "This C function processes a large array of floating point numbers in a loop. It's cache unfriendly. Suggest ways to improve memory access patterns for a modern x86-64 CPU." Codex would then return a range of suggestions, from using explicit prefetching instructions and vectorization techniques, SIMD intrinsics, to suggesting different data structures or algorithmic approaches like tiling or blocking. Each suggestion would be accompanied by code examples or detailed explanations. I'd then take these suggestions, implement them, benchmark the changes, and feed the new results and any remaining performance gaps back to Codex for further analysis. This wasn't a one-shot solution. It was a collaborative, iterative loop of prompt engineering, code generation, testing, and refinement. Let's get into the nitty-gritty of the kernel optimization itself. The target was a data-intensive cryptographic hashing kernel, crucial for a high-throughput network appliance. The original implementation, while functionally correct, suffered from severe cache misses and suboptimal instruction utilization. Codex immediately flagged several areas: lack of proper SIMD vectorization, inefficient memory loading, storing, and a branch-heavy conditional logic that disrupted instruction pipelines. Through our iterative process, Codex suggested 1. Vectorization. Asterisk instead of processing data byte by byte or word by word. Codex provided specific Intel SSE AVX intrinsics to process multiple data elements simultaneously. It generated code that loaded 256-bit or 512-bit chunks of data into vector registers, performing operations across them in parallel. 2. Cache optimization. It identified hot loops and suggested data prefetching instructions, along with a strategy to restructure data access patterns to achieve better spatial and temporal locality. This involved reordering array access and implementing a small, hand-optimized lookup table to reduce main memory trips. 3. Branch prediction hints. Asterisk for the conditional logic. Codex proposed using compiler hints, like _ built-in _ expect in GCC, Clang, and, more effectively, restructuring the algorithm to reduce unpredictable branches by converting some conditionals into branchless operations using bitwise tricks or conditional moves. 4. Loop unrolling and instruction pairing. It even suggested aggressive loop unrolling where beneficial, coupled with instruction reordering to maximize CPU pipeline utilization and minimize stalls, effectively exploiting instruction-level parallelism. Each of these was a significant improvement on its own, but the synergy between them, guided by Codex's deep understanding of low-level optimization principles, was what led to the truly astronomical gains. We were able to transform a kernel that was bottlenecking our system into one that barely registered on performance monitors. The final result? A staggering 232x speed improvement. To put that into perspective, an operation that once took nearly 4 minutes to complete now finishes in just over a second. This isn't just a minor tweak. It's a game changer. For our application, it meant a drastic reduction in power consumption, the ability to handle orders of magnitude more network traffic with the same hardware, and opening up possibilities for real-time analytics and security features that were previously impossible due to computational constraints. It literally redefined the performance ceiling for that particular component. This experiment